Hello, thanks for your interest in Fujitsu and Keysight joint interoperability test video. First, I would like to thanks i14y lab to give us opportunity. At i14y lab, we have opportunity to create and providing a vendor independent environment to promote the development of an innovative, open, and interoperable telco ecosystem. Moving next, I would like to first introduce myself. My name is Prabhat Prakash. I am technical consultant at Fujitsu, Germany. Uh, Brief introduction about Fujitsu ORAN offering. Fujitsu is one of the leading Open RAN vendor, and we are strongly contributing to lead the RAN transformation with open interface and disaggregation. Responding to our customer demands and accelerating the evolution of Open RAN globally, we have developed and delivered of the Open RAN compliant radio unit to not only in the Japanese market, but also in the US. As shown in the video, Fujitsu radio unit has full capability to realize the interoperability testing with other vendor, and operability of our radio unit has been demonstrated in European PlugFest 2021. We Fujitsu would like to continue contributing to improve the availability and operability of the ORAN and taking the lead in the open network. Fujitsu is responding to customer demand and accelerating the open RAN. Now I would like to introduce our colleague, Ingo Nickelheit from Keysight Technology, to introduce himself and talk about Keysight. So Ingo, over to you.
Yes, so also hello from my side. My name is Ingo Nickelheit. I work as a technical consultant at Keysight Technologies, a leading technology company that helps enterprises, service providers, and governments accelerate innovation to connect and secure the world. Keysight has introduced a suite of end-to-end solutions that enables an ecosystem of open radio access networks, ORAN vendors, and mobile operators to verify interoperability, performance, conformance, and security of multi-vendor 5G networks based on ORAN standard interfaces. And today we are going to focus on a solution verifying open RAN radio units demonstrated with this device from Fujitsu. Thank you, Prabhat.
Okay, so Ingo, maybe we can start with our slide 3. Okay, thank you, Ingo, for giving the brief introduction. Now, with help of slide 3, I would like to cover the RU part, how this our whole test environments look like. So so I would like to give some idea about OTIC test environment. At Fujitsu side, we are using single band 3.7 gigahertz 4TRX radio unit at German frequency. As you can see this in the picture, antenna 0 with total bandwidth of 90 megahertz and one carrier channel. The other antenna ports is not being used and terminated by 50 ohm termination. Ingo, if you can go to the next slide. In the next slide, you can see antenna 0 is connected to 30 watt attenuator to reduce the power level from RU towards the Keysight vector analyzer. Now, if you can move back again to the last slide, Ingo. Yeah, so the front haul optical cable, optical link connection is via 25 gigabits per second. Towards ODU emulator. Further on, as you can see, a LAN connection for RU maintenance port to connect this locally with Keysight equipment. Now I will ask Ingo to cover something more about this test environment from a Keysight perspective.
Okay, so the first thing we did, of course, was connecting the ORU to a programmable power supply that covers the entire range, voltage range of the support that is supported by the ORU, with a nominal voltage of minus 48 volts, then consuming approximately up to 950 watts. Most important for ORAN is, as Prabhat just mentioned, the front hall link between the ORU and the ODU emulator. As he said, for this link, we are using a 25 gigabit port, one of the ports that is available on the S5040 ORAN Studio appliance. Merging the M plane onto the front hall link, there is a 1 gigabit Ethernet to SFP connection between a standard NIC connector and the third QSFP port of the emulator. Packets from here will be merged internally with the F front hall link within the hardware processing of the DU emulator. By this, we are establishing a full link on the SM and CU plane communication between the two devices. Performing RF measurements, the RU's antenna port, as Prabhat already mentioned, is connected to the attenuator to reduce the output power suitable for sensible RF test equipment. We are not transmitting over the air. That's why we are connecting the cable directly to the RF in port of the receiver to perform the analysis. The vector transceiver can also be used as a source in the uplink case by using the RF out connector. Additionally, we see several clock and trigger connections that are used to synchronize the two instruments. The BXT vector transceiver module sits in a PXI chassis along with a precise frequency reference, an optional programmable attenuator that can be used, for example, in the uplink case, and an embedded controller, which is connected to the maintenance port for further debugging and demonstration purposes. In summary, the following Keysight components and software tools are used in this setup. S5040 ORAN appliance, which is essentially the ODU emulator platform. N7631 Signal Studio is used for the 5GNR signal generation. U5040 OpenRun Studio is the platform configuring and controlling the ORAN front hall interface. The M-Plane toolkit, of course, is used configuring and running the netconf client. The RF signal is then captured with an M9410 BXT vector transceiver and analyzed in the X apps performing 5GNR signal analysis. That completes the setup.
Okay, thank you, Ingo.
Yeah, if we just look in this in the picture here, we see first the optical connection going from the ORU here into this first port of the ODU emulator that sits here on top. The second optical port here is connected to a standard Ethernet port that is in the back side of the instrument. You see the additional connections, clock and trigger, that go to the RF equipment. And yeah, and then we have here the RF connection through the high power attenuator going also into the BXT analysis platform or instrument. And by using the empty slots here, one can easily expand the setup to support more than one RF antenna port, as we see there are 4, without necessarily consuming more lab or rack space in the setup. We can just add them here into the open slots. Good. So let's now continue with the test plan that we had for this demonstration.
Yeah, thank you, Ingo, for giving all brief introduction about the setup. Yeah, okay. So with slide the slide 5, I would like to just give brief idea what we are going to cover in the whole recording. So the whole test are divided into 3 category. The ORAN fronthaul configuration, RF performance, for fault management, and hardware related for alarm notification. So the IoT profile for RU is single band, NR, TDD with the nominal subcarrier spacing 30 kilohertz. With the FTT size is 4096. And total bandwidth is 90 megahertz with 1 carrier channel. So the open fronthaul configuration between ODU and ODU emulator and ORU will cover S plane, M plane, and CU plane. The S plane is we are validating the functional test of RU using G8000 275.1 synchronization. With CU plane, we are validating the correct timing is achieved with maximum and minimum fronthaul latency. And with M plane, we are trying to validate RU can get into service using session establishment procedure using hierarchical or hybrid mode. Successful demonstration of RU startup procedure in hierarchical or hybrid mode and some RU alarm notification we will try to cover in this whole picture. So on top of that, we will try to validate PTP synchronization loss in M plane and relevant alarm notification on RU side as well. So this is the whole picture we are trying to cover during this whole presentation.
Okay, so let's go into the demonstration directly and using the 3 steps that you just described. And first, let's set up the environment and the hardware to make measurements. So we have just seen on the slides before the hardware connections between the instrumentation and the device under test. I now brought up OpenRun Studio, which I said is our software environment, the user environment for the configuration of SM and CU plane to perform or to set up the ORAN link between the ODU emulator and the ORU. So the first thing we would need to do is actually to set up the hardware, which is here under the hardware setup. And we do have here our optical ports on the ODU emulator, and which I will turn on right now. That will activate the optical link. And we can also see now, as soon as it is activated, which particular SFP module is mounted into this cage. And we can open this, do further debugging, and that could be quite helpful if you connect the ORU and the ODU for the first time to check power levels and so on and so forth. We also can specify an arbitrary Ethernet address that is then used for the communication on the CU plane. And I can also, at this point here, turn the third port on, which again, I said I will be using later for setting up the M plane.
Yeah.
Again, here I also have the module information. The next step is maybe just jump to the ORU side. And what the ODU needs to know at this point is to know the MAC address of the ORU, which is given by Fujitsu in this case. And then that is the case. The connections are active. They see the green indicators here on the port status, which give a good sign that the physical connection between the two units is established. Now we can switch on or start activating the S-plane. To do so, under the time sync, I will turn on the PTP master in the ODU. As soon as I close this window, I see that the PTP master and the sync E also become green, which means they are active. Of course, in the background, it will also take a while for the ORU now to lock to this clock. And we can check this by monitoring the SFP interface, something that you typically can't do directly by using Wireshark, for example. But in OpenRun Studio, I can always monitor the traffic that is on the front hall link by creating a recording that will then be stored into a PCAP file. And this PCAP file can be loaded into Wireshark later. I have prepared this the setup as it could be seen, and maybe now share quickly.
So Ingo, it means that RU is turned on and connected to DU emulator. This is visible via 25 gigs indicator, right?
Yes, this is the basic physical connection is there. I'm already one step ahead since I have already activated the S-plane.
Can you show that the sync process has been established?
Yes.
To the audience, yeah.
So what we can do is first, if we go here and we go now into the interface monitor, we will see that there are now PTP messages already exchanged. There is nothing else than the S-plane in the moment, so there's only little traffic. If I create this recording, I can go into Wireshark, and there I will then see here the recording messages coming from your ORU asking for a PTP delay request and the responses from the server. I can, and I can look through the protocol here. It's basic PTP protocol at this point, but the synchronization is established.
Okay, so in brief, if you will go with the first front hall configuration, we can say that RU is turned on and connected to DU emulator. This could be seen by 25 gigs indicator, and sync process is successfully established, which also can be see via PTP synchronization indicator and at user interface. Also, the DHCP and M-play session is started. So we can see this in more details in context of validating S-plane, M-plane, and user plane functionality.
Yeah, exactly. So far we have started the S-plane, and the next step necessary to run the ORU is to configure it over the M-plane. So we also have to start the M-plane now, which is done through the M-plane toolkit. And the M-plane toolkit basically allows me to start the DHCP server and the netconf client, which I can quickly do at this point. So this one is it starts the DHCP server and with a predefined address. And this should respond now to your DHCP messages. Here I see that
I can see
ORU is now connected. And also in parallel now, I can also start the M-plane configuration that is executing a XML script that contains the entire call flow for configuring the ORU, which are a couple of thousands of lines. For this, I have also created or prepared a little slide so that we can see at the results. So if I would look into the log of the DHCP server that I just started, I will then recognize that your ORU unit has been provided with an IP address, as we have seen, and going into the M plane or the Ethernet port capture that is now established. I can also see the messages that are now going back and forth for the DHCP loan, as well as there are already messages coming in to start the M plane, which we should see on the next slide here. As I said, it's a very long script. You see that it's actually thousands of lines. And it will configure the entire ORU with the number of antenna ports, subcarrier spacing, and so on and so forth, so that everything is set up according to the IoT profile. We will also get here, because it's a normal startup, we will get the final information from the ORU that the full synchronization has been achieved and that it's fully in lock with the ODU clock. And then it starts running the supervision process. Yeah. So it keeps the two connected, and we are at this point basically ready to send CU plane data.
Yeah, perfect.
Okay. So yeah, while we've been talking through the slides, it actually has succeeded. Configure the plane. The supervision watchdog process is running. The next step now is to actually configure a signal, CU plane data, that is going to be sent over the front haul link. And to do so, we would like to create a 5G test signal.
Yeah.
To do this, we open the Signal Studio signal generation software for 5G NR signals. Let me enlarge this. And for convenience to do the setup, we can directly go and specify one of the predefined test models that are provided by 3GPP.
Yeah.
So for example, so we will have the bandwidth of 90 megahertz, as you say. We do have a subcarrier spacing of 30 kilohertz, so I can keep this. We work in TDD mode, and for most of the spectral tests, like ACLR, occupied bandwidth, as you see here in the help, we can use the test model 1.1. There are all the others readily available too. Then by confirming the input, it will automatically set all the parameters that are needed accordingly to generate a correct 5G signal. If I go into the channel setup, I here see the allocated resources within the frame and even here within the symbol structure. If this is ready, and this is all I need to do, at this point, I just save the setup, and I can then load the setup. A second, where's my mouse? This is the right one. Okay, so I can now go back into the ORAN Studio, and now from this 5G signal definition, I would like to create a ORAN frontal message stream. And then to do so, though, I go into the C-plane builder, because so far I only have IQ information. I would have to go into the setup of my CU plane and specify all the parameters here as of the number of antenna ports, compression, numerology, timing, and so on. Fortunately, for the demo right now, this will come as soon as I load the Signal Studio setup that I have just created. So with this, it automatically recognizes the setup that I have stored before. So for the compression scheme, for example, we are using block floating point with an IQ bit width of 14 bits. And we also have here the timing parameters that will become more important as we go into the delay management tests. And we have further options that define my VLAN ID, for example, that is used to distinguish those messages, for example, from the M plane. Also, we have a additional gain parameter here that accounts for the internal gain of the ORU. So this is all set here. Reading in the project, it knows already. It knows already what type of signal I'm looking at. So it has detected a downlink signal, 90 megahertz bandwidth, so on and so forth from the setup, and it's now I can now go and assign this signal to a specific flow, to a specific antenna port that I have. We're using the port number 8, which is actually the antenna port number 0 on the housing. If this is all done, I can build my PCAP file by exporting the data. So here I can export into an ORON stimulus file that will then generate me the PCAP data. To validate the EC3 traffic that is generated, I can also load this PCAP file. And we can see now here all the messages that are generated. And I can distinguish between my C-plane messages here that are necessary. I can look at the correct format of the message with all the EC3 header information, the EC3 C-plane information, then followed by all the U-plane data. And if I go into one of the U-plane messages now, and I pick one of the PRBs, I see the hex information, but maybe for me as a RF designer, I'd be more interested in the presentation of the IQ data. I can also look at the constellation here. So I know what my correct signal and stimulus looks like. I actually now want to stimulate the ORU and send this PCAP file to the ORU, which I do by opening here the player. So I choose the generated PCAP file. It will automatically change back to the interface monitor where I'm already sending back and forth S and N plane data already. But now if I turn on my player, you will actually see there is throughput There are more packages now, of course, transferred. And the throughput, of course, depends on the number of layers and the number of carriers and the number of antenna ports that I'm using. Then using more ports, it can of course go up to the 25 gigabits per second. And this now reflects a relatively simple test model, 1.1, and that is used for the spectral testing. So don't need that much throughput at this point.
Yeah, so Ingo, just for our audience, this throughput is for UDP traffic. This is
for the CU plane traffic, more or less, because the PTP and the M plane traffic doesn't really account. If I switch this off again, you will see that there is still some traffic, but this is very low. And if I would capture the communication now on the front haul link and go back to the Wireshark, for example, I will then see PTP messages, M-plane messages that are exchanged.
Okay.
The majority of the throughput actually is then generated by CU plane traffic. Okay, so at this point we have validated the EC3 format and the data that is sent over the front haul bus. And the RU at this point is fully configured and should be running.
Yeah.
Which takes us to the next point then of the RF testing.
Yeah, RF testing. Yeah, we can go back to RF testing.
Okay, so now I would have to change to the RF instrument.
Please go ahead.
Yes. So we are now running the software that is on the VXT vector transceiver, now getting the RF signal from the ORU. And in here, I now have possibilities to run 3GPP compliant RF testing. And as you can see here from the list, there are those tests that are defined in the standard, like the channel power, the occupied bandwidth, ACPR, which are spectral measurements, and we will see in the second step also some modulation analysis. So here I'm measuring the channel power, for which I do have kind of the same convenient presets that we have seen during the signal generation. So I basically specify the bandwidth and the mode, and then the test model, and all the settings that are needed are automatically adjusted.
Yeah. Okay.
So by doing so, at this point, I can measure the power in the nominal 90 megahertz bandwidth, which is around 11 dB now, plus some cable loss and plus the attenuator. We end up at roughly 45 dB output power for your ORU.
Okay, yeah. In brief, that RU transmit the RF signal with nominal power of 45 dB, which is further attenuated by 30 dB attenuator. Plus, I think we have a 3 dB around cable and connector loss. So we have some additional losses. So we expect the measure bandwidth, band power of around 12 to 11 dB. And we can see the corresponding value over here.
Exactly.
Yeah.
Exactly. And for the completeness of the RF measurements, I do also have prepared here the overview now of the different types of measurements that we can run. So again, here we see the total carrier power here, roughly 10.8, 11 dB, which fits well with our expectation. And the occupied bandwidth is also, it's 87.3, which is also within the expected range. And you can also see this quickly by inspecting here the pass parameter. So it knows the pass-fail criteria and
Yes.
immediately report it. And then we also have here the ACPR test for the upper and lower sidebands, which are also within spec what we would expect. But those are those three kinds of spectral measurements that are readily available by choosing here the measurement function and then applying the parameters by setting the right test model. So for the next step, I would like to take this a little bit further and now do some EVM measurements. For this, a higher level test model is defined. So we would be using the test model 3.1a.
3.1, yeah.
Yeah, so I can, in this case, directly load.
And what will be the modulation scheme over here? It's 256 QAM?
It's 256 QAM, yeah.
Okay.
So I will load, now load the other test model. And if I go back to my RF measurement, that one is still running. And I go here into the modulation one. So now, yeah, it's already demodulating the signal. It's the same principle as we have done it before. So I have here the modulation analysis. And then I also have here my measurement setup,
yeah,
which I adjusted to the correct test model here. And now we have the constellation. The constellation visibly reflects the good EVM that we have, around 1%. I also see the allocated resources, which should match what I had in my signal setup before. I also see that this nicely matches with the time domain waveform that I capture. And I also can get from here some necessary measurements, like, for example, the frequency error, which is defined.
Yeah.
And that should be within a few ppm range. And you see this here is within tenths of hertz compared to 3.5 gigahertz. So it's pretty good. So all of this is also within the range of expectations and for a very good RU unit.
What should be the range for IQ data offset? It should be what will be the nominal value for that?
Well, it's pretty low. Actually, I mean, with minus 70 dB, you almost have no offset between I and Q, and because you are using digital inputs,
yeah,
more or less through the front hole bus, then you don't have any IQ offset a lot in the baseband generation there, and the IQ offset that is due to your RU unit modulating the IQ signal then is pretty good.
Yeah, yeah. Okay, go. So we have done our CU part as well. So now you can take it further through M-plane or.
Yeah, we will now. Well, we will do some conformance testing now that we know the RU is working correctly. Let's now go a bit to the boundaries and check the timing.
Okay. Yeah.
Management.
Sounds good.
Delay management as an example for the RF testing.
Okay. Yeah.
So To do so, we will go back here, and we will load the TM1.1 or 3.1a test model. The important point now is here under the configuration and the timing tab. I now have here all the controls that are defined in the spec and in the IoT profile accordingly, and to define the delays on the front haul bus. There are several tests defined that one can run. We have decided to perform a typical one, which accounts for the front haul latency, which is here the relative delay of the front haul bus. And there's some definition that it should be between 0, or if the RU can't handle 0, the minimum value that it is capable of, and the maximum value that it can do, which varies from RU unit to RU unit. In your case, we know from the IoT profile that a delay of 127 microseconds is supported. So let's see what happens if we go to 128 microseconds. That will now change the timing of the PCAP file that is generated. And again, if we go back here into the stimulus that we have generated before, you see that there is some time advance in everything. So changing this will have influence then on the latency of the front haul bus. So if I can now load this stimulus, there's still something running, of course. And I've done this with the test model 1.1, I believe.
Yeah.
Yep. So again, I start playing this file. And I believe if we go back to the RF testing, we now see that we can't demodulate the signal anymore really well. And you also see that the spectrum is now incorrect. So something with the packages that we are sending is not okay. So that is one sign to validate or verify that there is something wrong now on the front haul bus.
Yeah.
That's one way of testing. The other way of testing is with focus on the front haul link itself. So I can again go here and create a recording, a capture, and now load this recording into more detailed CU plane and analytics. And I've already prepared something here that already has all the windows set up. So that will then look like this. So I will again have all the captures packages that I have on my front haul bus. And now from here, I do have timing measurements. I have a ladder view where I can much more in detail go through the entire capture data and perform analytics on this capture. And for example, in comparison to the normal case, so where the timing is still correct, there is now some latency that I can detect here in the duration of the slot. So that is something that can pinpoint to the problem that I'm having.
Yeah.
So I can use the further front haul analytics to also do some debugging or analysis on this delay management. test, which is also something that is required by the test procedures. Okay, so that was also an example, how I can go from the operation of the ORU now into more specific testing of the conformance and IoT capabilities of the RU.
Yeah.
As you mentioned before, we now have to take a look at the M-plane, which is also part.
Yeah.
Okay, so for testing the M-plane, I will go and call some specific call flows that for example will help me to detect an error case. In this case here for the fault management. Instead of starting the default call flow as I've done before when I started the M-plane, I will just execute this script here that does not much more than a basic configuration, bringing up the M-plane and then waiting for some alarm. If I do run this one, and then I go and then I go and switch off the PTP.
Yeah.
Your RU should actually throw an alarm, and
Yes.
that is the case. It just takes a while to execute. Again here. This is if I execute and start the M-plane just with this basic configuration. Again here, what's important is that I see the PTP state locked initially. I'm also now using the maintenance port on the RU as a control feature here. I can also see that the PTP is completely locked. Now I switch the PTP off as I have just shown. And what will happen is, your RU will report you're losing the lock. It will send a notification that there is a control synchronization error, which I can then, of course, interpret in my netconf client that I have received the alarm that I was waiting for. So my alarm generation test has passed.
Yeah. So in that this process will turn PTP synchronization check at M-plane logs, and corresponding notification will be sent.
Exactly, and this is the validation of the test that needs to be achieved.
Yeah, that's right.
And
so
because we don't have
yeah, go ahead, please.
Because we don't have the hardware available to show in the moment in this remote testing, I'm also using now the debug port to take a closer look at what happens in your RU.
Yeah, that will be a good idea. So yeah, you can just log into the debug port. That way we can show that how we can connect our maintenance port via Keysight equipment. Yeah.
Exactly. So again, I'm just connected through through the embedded controller, which is nothing else than a normal PC.
Yeah.
And I can do a normal, what is it then, a telnet or a login, and then I can probe the individual ports that interfaces that are available in the RU. So for example, corresponding to your notification in the M-plane saying I'm unlocked, I can also see this state here in your maintenance port. It is unlocked, the PTP is free running, there is no sync state.
Yeah, perfect.
Normally, if I have not connected the maintenance port, I will see it in the M-plane, of course, but also on the hardware, there is some indication. So there is a LED indicator. And now this one actually starts blinking red, which is a sign that there's something wrong.
Yeah.
It is actually a major fault state. So I know that, that there's something going wrong. And by using the maintenance port, I can, of course, look now in more detail what the root cause is. So it reports a front-haul synchronization error, which is exactly what it reports in the M plane.
Yeah. So in nutshell, like the second screenshot has been taken from our Fujitsu radio unit through via maintenance port, and you can see that how the PTP lock state has been shown over here. It is PTP shown is free run, and synchronization state is unlocked, and physically if you can go and see the LED status, it will be shown as a red blinking with LED status 2 is green on. Apart from that, the main point to discuss is to show over here is that front haul synchronization error is shown as active. So these are key aspect we have checked at the Fujitsu radio unit from the maintenance port, and this is aligned with and the same message has been already sent via M plane to to Keysight emulator. Yeah.
Good. So yeah, so that concludes the demo overview of the sample tests that we've been running to demonstrate the operation of the ODU emulator together with your ORU.
Yeah, perfect. So so this is concluding all the tests we are trying to cover using this demo. So thank you, Ingo. Thank you for your time, and thanks for all your effort to bringing this picture in a nice manner so that we can minimize the recording time, and it will help help our audience to give. To go through the Fujitsu and Keysight joint partnership, and hope we can go through some more interoperability test if the time will permit. Thank you, Ingo.
Yeah, thank you for the opportunity to work with your ORU and completely also validate the entire flow that is enabling a complete conformance and an IoT test together. And I'd say, yeah, there's certainly more to come. And if we go to higher MIMO orders and new features that are implemented on the ORAN front haul and the capabilities of the RUs that are going to come soon. And yeah, then we will continue this series of demonstration. At first, this testbed that we have with the RU and the ODU emulator enables the setup, the configuration, and the verification of the S plane, the M plane, CU plane of the entire front haul link. And as we have seen here, we do have this S plane data. And first, we bring up the M plane, and we can also look at this EC predator that is on the front haul bus. In the second step, we sent down link test models and validated the RF performance either in the spectral or in the demodulation domain. And then verifying the ORAN conformance and IoT, we validated the boundaries of front haul latency and M-plane alarm notification, which also is indicated on the hardware.
Perfect. So in that way, we are concluding our demonstration, and I would like to thanks everyone. Thanks our audience to watching this video. Thank you. Thanks, Ingo.
Thank you. Thank you all.
Thank you.
Bye-bye.
Bye.